Hi everyone, welcome back to our YouTube channel, Becoming a ROS Developer. I'm Desire, and today we've got Nahl, who has just completed the course Linux Basics for Robotics, and she'll be giving us a presentation on that. So first of all, we'll begin by seeing her code base running on the real robot, and then after that we'll get into the details about how she managed to do her project and get to ask you a couple of questions as we go. So without any further ado, let me now hand over the platform to her so she can begin her presentation. Alright, Nahl, whenever you're ready.
Yeah, so I'm just waiting for the real robot lab to open up. But basically what I'm going to be doing is, as soon as the robot lab opens up, I'm just going to open a bunch of terminals and connect to the robot. We're going to test with the teleop first, whether or not I'm connected, and then I'll run my script. So I'm just going to wait for the robot to...
Alright, no worries.
So you can see the window here. I'm just going to make that a little larger so it's easy to see. So first thing, I'm just going to log the real robot and another terminal. I'll keep the visualization separate because I don't think we need that right now. So
Yeah, we won't need Gazebo.
Yeah. So I'll just quickly access. Just waiting for that to get ready, and then over here I'll do the same thing. I'll just connect to both the optical avoider and the distance strip. Alright, so I've started the optical avoider. See the results of that in just a second. So I'll just run the first. Okay, so we've already started turning because we're pretty close to the wall there. So I'll go through the logic later, as you mentioned, but the main difference between the code that I implemented and the code that was asked to be implemented by me by the instructions in the course was I experimented a little with like compound movements. The biggest thing that I noticed is it's quite a lot slower than I expected it to be at first, and obviously this is due to various reasons like the latency, the connections, and all that. And also the speeds are pretty slow. It takes quite a while. So as you can see here, I have a movement called moving forward and swipe right. And what I've done here is basically I've tried to group together two movements so that it's faster and easier to like finish a full track or avoid obstacles.
Right.
Right now it's moving forward. So the times when it does move forward and swipe right, there's another one moving forward and swipe left, is when both the front and the front right sensors are free to move. So the reason I did this is because in the original code, they asked us to only implement moving right or moving left when both sensors are free, and I noticed that that was quite slow as well as sometimes not really effective because we would just dance around. There's also I actually have a presentation which I'll go through in just a second when I'm explaining the logic of the code.
Right.
As you can see here, it's working. It's pretty slow, but it does seem to work. It's avoiding the wall there. It's gonna go straight. So yeah, so you can see it's pretty close to the wall, but it still has space to move forward. So I decided to move forward and swipe left. So it moves forward first, and then I set the angular velocity for it to move. If you don't mind, I could start going through the code, or would you like to see it run a little longer?
I think let's get through the slides now, and you can explain in more detail there. I think we've seen it avoid obstacles. That's pretty good.
Yeah, we'll come back and see if it avoided that well. So.
All right.
Yeah. So the first thing is obviously writing the bash script. So the main thing I struggled with at first was if statements with the logical and operator, because throughout the course the if statements that we were writing were pretty basic and weren't really compounding multiple variables. So I had to learn the syntax for that. Calling the get functions, making sure the syntax is correct, like white space matters a lot as well, and then obviously using the relational operators. So for the logic and testing part of this, I did a total of 3 main testing phases with the gazebo simulation first. So in the first iteration, I followed exactly what the project gave us, the structure that they gave us, and I saw that it worked, but it was sometimes with big mistakes, like here. As you can see where it would turn right a bit too much, which is what led me to think about, thinking about compound movements instead of just having it turn right. Maybe it can move forward as well. So that's not the best. So I wanted to make it go, more around the track while still being able to avoid obstacles.
Yes.
I also there's an angular velocity you can set. And so I did the calculation based on the script that they gave us. I think it was in radians per second, it was 0.3 radians per second, so a 1.5 seconds through time. It's about 27 degrees. So I thought, hey, why not try 90-degree turn angles? But it ended up being way too sharp, and it didn't work. And I also forgot to reset my velocities all the time, so I did that. In the second iteration, I had an issue here where the robot got stuck against the wall. And so I was like, hey, if we're moving forward, what about moving backward? But that didn't work too well as well. It just made the whole track a little bit longer. And then this is when I experimented with the compound motion, which I'll go into later. And then in the iteration 3, I refined the compound movement a little bit and then removed the backwards motion. And then I'll talk about this negative timing issue in just a second. So you go back here, you can see it hopefully did avoid the wall. You can probably see it in, it's disconnected, but you could probably see it, yeah.
Yeah, please.
I'll go through the code here.
All right.
Okay, so I'll go through this main script first. So this is the obstacle border script. I basically followed the structure that's given in the instructions. So first thing, we're just calling the robot function library, because that's where all our getters and setters are, so the variables that we need to be able to access in our scan. And then we're just making sure the robot stops initially. We set a threshold. This is just the distance that we want the robot to be away from the wall when it stops its movement. So for example, it used to be always 0.3 meters away from obstacles or the wall. This is what causes it to stop. So we have our values here where we're just getting all our values continuously. So these first are just simple, we're getting the values from the sensors. But down here, we're doing our first set of comparisons. So these 3 are Boolean variables. So we're basically checking if the range that the sensor is reading is more than the threshold, and if it is, then you're free. We'll store a 1, which means that you're free to move for that direction. So we do the same for the front left, front right, because that's where the robot is sort of interacting with everything. Over here, just for myself, I like to print out all of the ranges and also the freedom ranges so that I can see that the code is actually making decisions correctly.
Yeah.
So I can go in and see, for example here, that it's all free, so it's moving forward.
Yes. Okay.
Here are just 8 of the if statements. So there's 8 different cases here because I'm using the front 3 sensors to dictate which direction I'm using. And then if I want more controlled movements, I'll go to checking the other 2 front sensors, the left and the right.
Right.
So here we've got the front left, front, and front right. And if they're all blocked, then we want to check whether
Right.
We're just putting in a simple if statement, and then on the left, it's the left lane has no leeway and turn right.
Right. Can you tell
This is
me?
the
Can you tell me something? Sorry to cut you short there. So, how do you determine when you have to switch from checking one index to switch to checking two? Right. For example, let's say you had two ones, so that means you have two that are open, two open slots, so maybe front left and front, right? So instead of just checking one, like front only, how do you choose, how does your algorithm choose to checking two instead?
Okay, so I have a separate if statement for if they're both. So we're just doing a bunch of if statements here. So for example, here I have the front is free and the front right is free.
Mm-hmm.
And so this is the compound movement that I was talking about.
Okay.
So
Okay.
instead of checking the left and right sensor and being like which way can I move, I just know that since the front is already free, it's better for it to just move forward first. So I let it move forward first, and then based on this case, for example, the front right is free, so I know that the right is more free than the left without having to check, the second sensors, the second other two sensors, because I know from these values right here that there's no way that the left is going to be free enough. I set the right angular velocity over here. You see the value is slightly different. This is half of the other value, so this is like 14 degrees.
Yeah.
Because we want the turn to be a little less sharp.
Mm-hmm.
So that's how the algorithm works. It's not too complicated, but we're meant to keep it simple anyway. So.
Mm-hmm. Mm-hmm. All right. So you're sort of like narrowing down what's the number of possibilities. So you first eliminate the very first one, you're setting that it's blocked, and then use the remaining two to determine whether you need to go forward with some angular velocity or just keep going forward.
Yeah, it's exactly like you said. So the first thing, my front sort of line of defense are all the front sensors. So the front sensors, because they're closer to where the robot is like walking towards or going towards, those are going to tell me my base information for which sides of the robot are free. So if I know, for example, that my front left is giving me a block signal, I know that there's no need for me to check the left sensor, because there's no way that the left sensor would be free enough for it to move. So yeah, I basically filter through with the front sensors first, and then after that, if they're all giving me free, I can then refine further with the left and right sensors.
Okay. All right. Very, very impressive. All right. Let's go on.
Yeah, so I want to talk about the issue mentioned here, which is the negative time issue due to delay adjustment. So you can actually see a couple error messages here where it says sleep invalid option, and I'll talk about why this error shows up and what I tried to do to fix it. So as you can see in the code that we were given for the example code in the simple control.bash, we were asked after calculating the time to move based on a speed of 0.1 meters per second to subtract 1 second from this time for the delay. It said it's because after you set the parameter, you'll get a delay. But the issue with this is sometimes your time to move can be less than 1 second, so you can get like half a second to move. And so what this does is you end up with a negative time.
Right.
And so when you try to call the sleep function with a negative time, it'll throw this error out here. Now, thankfully for my situation, even with this error, the amount of time that it takes for it to realize the error and then stop is actually sufficient for me not to have to touch it. But the error was still bothering me, so I had a copy here where I added this simple if statement where I'm checking if the time to move is less than 1, which means that
it's a negative value.
It could be a negative value, that I want to recalculate the time to move as the new value, and then it will just sleep for that amount of time. Because if the time to move is less than 1 second, I don't think I should have to worry about the parameter setting delay.
Okay.
Yeah, and if the time to move is more than 1, then we can just let it pass and just use the original time to move that it calculated. The issue with this is it didn't end up working as well. It was still avoiding obstacles, but it ended up going in circles around, so it would turn left a bit too much. It's just, I think it's a nuanced thing, like a small detail where I would have to work on this even further.
I do like that approach. What I would want to know is what happened. Did you try like reducing the angular velocity as well when the time to move was that small?
Yeah, so I tried a lot of things. So the first thing was actually reducing the speed, but reducing the linear speed is not a great idea at all because the speed is quite slow to begin with.
Mm-hmm.
So then I decided to play with the angular velocities. Like I mentioned, I tried larger angles, so like 90 degrees. I tried smaller angles. The issue with going even smaller than 14 degrees at the minimum, which is where my current script
Mm-hmm.
is that now it needs a lot more iterations when it's not in like a super blocked position, right? So it takes a little bit longer
To decide,
like
okay.
right now. It not only to decide but also to complete like a full track. Like it will have to turn right maybe 3 times in order for it to finally like avoid a wall.
Mm-hmm.
So yeah, I bet I could fix this issue if I did a little bit more testing. But for now, I think it's not too bad.
Yeah.
It seems to be working somewhat.
Yeah, I think it's working quite smoothly. So it's just that I was thinking, would would minimizing the amount of angular distance that it is to cover, or would minimizing the time that it's turning help to at least deal with that turning too much issue? But yeah, it's fine. It's fine. I think for now it works pretty well. All right, so you can go on to the next one if you still have other things you want to talk about.
Yeah, I think that's all for the obstacle avoider.
All right.
Bit of it's a simple script, but here's robot statistics.
Yeah.
This is even simpler. Over here, we're just dealing with all the getters and subset setters from the robot function file over here.
Mm-hmm.
So we're basically just calling those functions and then just printing them out. So we're getting our distances, printing them out, all of our directions. So you see here, it's printing everything else from the distance, the direction, our roll pitch, draw values, our direction and speeds and all of that.
Mm-hmm.
So it's a pretty simple file. There's not much happening there.
Yeah.
Just go back there. It's been blocked by the Zoom.
Oh, sorry.
So yeah, we're just calling everything.
Okay, all right. I quite like your obstacle avoidance script, so I think if you don't have any other script you want to look at after this one, we can go back to that one. So
Yeah.
all right, so let me look, which one did I want to speak about? All right, we've got right. Okay, so yeah, I was thinking about the logic that you spoke about, the compound movements aspect of it, right? So I personally I like that because that stops the robot from turning in the spot, right? When you can turn and be covering distance at the same time, I think that is quite nice.
Yeah.
But I want you to give me some more detail. Like, what did you end up deciding? Did you end up figuring out that compound movements were not helping at all? Or because I don't, in the current demonstration that we see, right, we don't really see it do as many of those compound movements where it turns and also covering linear ground as much, right? So can you can you explain to me what made you revert to this stop and turn again?
Yeah, so the way that I decided was, at first, the compound movement itself, I experimented with different kinds of compound movement. So the first one was where you go linear first, and then you set it back to, you go linear back to 0, and then you set the angular and let it turn.
Mm-hmm.
I also experimented where I set the linear and the angular at the same time, so it was sort of like moving, like, not, like it was like curve moving, like it was moving in a curve because it had both angular and linear speed.
Yeah, that's
with that I faced some issues with that where it would sometimes go into an obstacle, and like because there's different times for the time to move for the linear and the time that we want the angular to go to reach a specific angle. So I decided to separate those two. And in terms of not implementing the compound movements for all of the rest of the script is because here, if we go here, for example, the way the logic works is if everything is blocked, which means it can't move forward either, we just turn left or right,
Mm-hmm.
If we go, for example, here, let me go to one where I can show you where I didn't implement the compound movement here. The turning left. The reason I didn't implement compound movement here is because we can see that the front sensor is blocked. If the front sensor is blocked, it means it can't move forward because the distance is less than the threshold. And so what this comes down to is basically, I want it to be safe, even though, as you can see in the actual movement here, it is more, like for example, right now, yeah, it's moving forward because all of them are free. In this case, because all of them are free, I decided to just let it move forward instead of turn left at the same time.
Yeah.
Yeah, so over here, for example, it can only turn left because the front is blocked. So I just wanted to keep safe there. So the only times where I let it do this compound movement is when more than one front sensor was free. So for example, here the front left and the front is free, so I know I'm good to go for a compound movement.
Okay, I see. All right. That's pretty good. All right. So let me just ask maybe some very general Linux questions, right? So you probably know this, but it is very important thing to at least have a general idea. So the purpose of bash scripts in general, right? We know we can use them in this way, but what do you understand is one of their most significant aspect in robotics in general? Besides having to, go ahead.
Yeah, because with bash scripts, the main thing is whatever you can run in the script, you can run in your terminal. So maybe sometimes if you're setting up a project and you're having to run like the same 3 commands each time, where you're navigating to a certain file and then you're giving certain permissions, you could just turn that into a bash script and then just run that single bash script to set up your project instead of having to run like 4 or 5 different commands manually in your terminal.
Yeah.
That's where I see the most like utilization for a bash script.
Yeah.
To compound everything together and make it more efficient.
Yeah, correct. And all right. Yeah, I think that's it from my end. I really liked your implementations, particularly for the obstacle avoidance. The one last thing I'd like to ask you is, have you considered, okay, you have been considered 3, so front left, front, and then front right? So you've been considered those laser indexes, right? And did you at any point get, I don't know, is it an epiphany or something? Did it come to your mind that at some point your robot might register that either front and front left are both free, but its size won't fit, right? So as a result of the placement of the sensor that we're using, it is in the center of the robot, right? But it has extensions to both to the left and the right? So if your sensor picks that the front and the front left, for example, are both free, but the front right is closed, but its own radius does not allow it to rotate enough to avoid the obstacle, did you get a case where that was a problem? For example, with particularly movable objects, because they are tiny, so you get one sensor that picks a value, but the other ones pick no obstacle. They consider the other side to be not closed, but then when it tries to turn, either the left wheel touches or the right wheel touches. Did you get to experience those? And if you did, how did you deal with them?
Yeah, so I ran a lot of my testing in the simulated environment, so I didn't run into that issue as often. In terms of running into that issue with the real robot, though, I think I've only tested with the real robot like 3 times.
Yep.
And I remember the second time I was testing, this was when I was experimenting with the compound movement. I did run into that issue once where it was in front of those little logs, which I can show you. Right. This is an example right here.
Yeah, exactly. Yes.
Where it's moving that log. And I tried to think about ways I could fix that. But I think the best way for me to have done that, first I tried changing the threshold value. So I tried increasing the threshold a little bit more.
Yeah.
I could maybe give myself a little bit more leeway for it to turn. I don't know what the size of the machine is or the size of the robot is.
Yep.
If I was there in real life, I think with a lot more like real robot testing, I would have been able to zero in on a threshold value that's larger, but still, close enough where we're not stopping like half a meter from the wall. So I remember I played around with 0.4 and 0.5, and I didn't run into that issue again, but the new issue I was running into was now that it was stopping a bit too early for like the edge of the wall.
Yeah, yeah.
Fixed thing. So I think that's an issue that I would be able to solve given more time with like real robot testing.
You still run into the same issue if you are running it in simulation, for example, with the like rectangular prism obstacles, right? You still get into that issue there as well. That's why I was asking, because it's quite common, and I just wanted to see your approach to it. So I personally would also consider like seeing what the increasing the threshold value would do, right? It's obviously one of the very big ones you can like just blatantly use to solve that issue, but then you also have this stopping too early issue. But yeah, it's a good thing to keep in mind, because you always encounter obstacles that have got bodies that are not just point masses, right? So yeah, just wanted to see your approach to that. So well done on picking the threshold value as one of the main parameters you can tune. All right, that's it from my side. So I think we'll wrap it up here. Very nice presentation, Nahl. It was quite detailed and well explained. All right, so we'll just hang around and we'll finish the conversation as we can. Alright everyone, this was Nahl's presentation, and a warm congratulations to her. Very detailed explanation, well thought project, and would like to encourage all those of you who would like to also come and showcase your work to give a shot to the courses that we offer certification on. And until next time, keep pushing.